Welcome to the second module in our series on petroleum production engineering. The inflow performance relationship introduced in Module 1 is the production engineer's shorthand description of a reservoir's performance potential at a given average reservoir pressure. It is the relationship between the bottom hole flowing pressure and the flow rate, and is the starting point in the analysis of well behavior. Inflow performance is the major contributor to the production process, yet our knowledge of the factors that control it and the way it varies over time is inexact because of the numerous variables that can affect it. While it is the first link in the chain of our production system, it is unfortunately the weakest link. In this module, we will look at some of the techniques currently used for calculating IPRs, learn some of the basic assumptions involved, and see how IPR curves are applied in practice. As we discussed in Module 1, a flowing well never achieves its maximum pumped-off potential flow rate. Pressure losses in the tubing, chokes, and other surface equipment make it impossible to get the pressure opposite the formation down to zero. The bottom hole flowing pressure is equivalent to the back pressure exerted by the flowing column of liquid as it moves to the surface. These flowing pressure losses above the formation are usually quite large. The inflow rate against this back pressure is not a true reflection of what the potential rate might be after installation of artificial lift, because artificial lift lifts the load and reduces the bottom hole pressure. It is important to know the true relationship between the bottom hole flowing pressure and flow rate, even down to a very low pressure. Therefore, the production engineer must define the IPR and predict how it changes with time.
First, let's look at some of the factors which influence the shape of the IPR curve. The flow rate, Q, out of the formation, is primarily a function of the pressure drawdown. That is, the difference between the average reservoir pressure and the bottom hole flowing pressure. For a given average reservoir pressure, then, each bottom hole flowing pressure corresponds to a flow rate. We plot this function on a pressure flow rate graph, like this. When the bottom hole flowing pressure is equal to the average reservoir pressure, there is no flow. That is the point on our graph where P sub R bar equals P sub WF, and the flow rate, Q, is 0. We continue plotting the IPR by reducing the bottom hole flowing pressure, that is, increasing drawdown. As the bottom hole flowing pressure is reduced, the flow rate into the wellbore increases. As the bottom hole flowing pressure goes to 0, the flow rate reaches a maximum value. This maximum flow rate is referred to as Q prime, or the pumped-off or open flow potential of the well. As the well is produced, it is likely that the reservoir fluids will be depleted, and the average reservoir pressure will gradually decline. At some future time, there will be a new lower average reservoir pressure and a new IPR curve with a lower Q prime. The IPR curve shrinks as more fluids are produced until the pressure has dropped to a point where the well no longer flows. As we recall from Module 1, the productivity index, J, is related to the flow characteristics of a specific well. J is equal to the flow rate Q divided by the drawdown, P sub R bar minus P sub WF. IPR curves have different shapes for different reservoirs, depending primarily on the drive mechanism of the reservoir. A reservoir with a strong water drive or a solution gas drive above the bubble point will have a straight line IPR. In the special case where the IPR is a straight line, J equals the reciprocal of the slope of the IPR and is constant. For a solution gas drive reservoir, the straight line portion above the bubble point reflects the dynamic flow characteristics of single-phase liquid flow through the formation. However, when the flowing pressure falls below the bubble point, gas comes out of solution, reduces the permeability to the oil phase, decreases the productivity index, and reduces the oil flow rate within the formation. Remember, the relative permeability to the oil phase is dependent on the oil phase saturation. At increased production rates, P sub WF has lower values, and more gas comes out of solution. At higher gas saturations, the relative permeability to oil drops further. This results in a downward curving IPR. In other words, we have a steadily decreasing productivity index at increased production rates. Other factors such as increased oil viscosity, rock compressibility, and turbulence can add to these effects as wellbore pressures fall and rates increase. We conclude then that a solution gas drive reservoir below the bubble point has a downward curving IPR. Often, a well's IPR curvature is intermediate between a straight line and this classic solution gas drive curve. In such cases, the average reservoir pressure is receiving support from gas cap expansion, or a water drive.
A number of acceptable techniques for estimating the shape of the IPR curve have been developed. We will discuss two of them in detail here. The first was suggested by John Vogel in 1968. The second by Michael Fetkovich in 1973. Vogel's main objective was to simulate two-phase flow through a reservoir into a wellbore. By analyzing a number of different solution gas drive reservoirs, he attempted to establish empirical relationships which could apply to all such reservoirs. The computer program that he prepared solved the equations of flow for somewhat idealized reservoirs.
For example, it assumed that the reservoir was circular, completely bounded, and with a fully penetrating well at its center, that the formation was uniform, isotropic, and had a constant water saturation, that gravity and compressibility could be neglected, and that semi-steady-state flow occurred. Vogel simulated reservoirs covering a wide range of conditions. These conditions included differing reservoir relative permeability characteristics, as well as the effects of well spacing, fracturing, and skin restrictions. Analysis was limited to flow conditions below the bubble point. As depletion occurs in a solution gas drive reservoir, the productivity of a typical well decreases. This occurs primarily because the reservoir pressure is reduced, and because increasing gas saturation causes greater resistance to oil flow. The result is a progressive deterioration of the IPR. The values on the lines reflect the percentage of reserves produced. Vogel took the important step of plotting each curve as dimensionless IPRs or type curves. We obtain these curves by plotting the bottom hole flowing pressures divided by the average reservoir pressure on the vertical axis. Then on the horizontal axis, we plot the production rate divided by the maximum flow rate, Q prime. When this is done for each curve, they are replotted. It is immediately apparent with this transformation that the curves now are remarkably similar throughout most of the producing life of the reservoir. After analyzing 21 different reservoirs with various crude oil properties, relative permeabilities, and wellbore characteristics, Vogel found that IPRs generally exhibited a similar shape, as long as the bottom hole flowing pressure was below the bubble point. For this reason, he developed a standard reference curve, which can be used for all solution gas drive reservoirs. This standard curve is shown here. It does not imply that all reservoirs are identical, but that this curve may be used as a reference standard for all reservoirs within a tolerable error. This reference curve is described exactly by the equation given here. Note that Q is the producing rate corresponding to a given bottom hole flowing pressure P sub WF. Q prime is the well's potential at 100% drawdown, and P sub R bar is the average reservoir pressure or the bubble point pressure, whichever is lower. In order to illustrate the use of this curve, let's assume that a well is producing 1,172 barrels per day at a bottom hole flowing pressure of 716 psia. The average reservoir pressure is 1,420 psia and is below the bubble point. We are asked to construct the specific IPR for this well. First, we calculate the dimensionless pressure. It is equal to 716 divided by 1,420, or 0.504. Using the type curve, we find the corresponding dimensionless rate, Q divided by Q prime, or 0.696. The well's potential, Q prime, is equal to 1,172 divided by 0.696, or 1,684 barrels per day. The type curve can now be made into this well's IPR curve simply by adding the values for average reservoir pressure and Q prime at the appropriate endpoints. The scale of the graph is now established, and any desired point can now be read. Remember that Vogel's results are only for the curved portion of the IPR curve, which exists below the bubble point. Above the bubble point, the IPR curve is a straight line, and we can obtain its shape by drawing the tangent to the curve at the bubble point pressure and extending it to the original average reservoir pressure P sub I. The extrapolation is shown here for our sample problem.
In order to determine the shape of the IPR curve at a future average reservoir pressure, we need to know a single bottom hole flowing pressure and its corresponding flow rate at that average reservoir pressure. Using our dimensionless curve and a data point, we would repeat what we have just done. This would yield a second curve. The difficulty is that we do not have well test data at some future unknown average reservoir pressure. That will be our next subject for discussion. But now, let's be sure that we understand Vogel's technique. With Vogel's type curve, one flowing well test, and a value for the average reservoir pressure, we can obtain a single IPR curve for our well. But what about the future? How are we going to obtain the future IPR curve using Vogel's method if we do not have the test information at some future average reservoir pressure? That is the same question Marshall Standing asked in 1971 when he published the results of his work. Let's take a look at it.
We remember that the productivity index J is defined as productivity index equals the flow rate divided by the drawdown. If we substitute J into Vogel's equation, where the average reservoir pressure is below the bubble point, we obtain this relationship, which gives J, or the productivity index, in terms of flow rates and pressures. If J could be calculated for some future average reservoir pressure, the pressure and flow rate values needed to find the future IPR curve could be determined. Standing suggested that in the limiting case, that is, where there is very small drawdown, bottom hole flowing pressure would tend to be equal to average reservoir pressure. That is, P sub WF over P sub R bar would tend to unity. So we have a limiting value for J, referred to as J star, which is equal to 1.8 times flow rate divided by the average reservoir pressure. We see J star depends on the specific values of Q prime and P sub R bar. Now all we need to know is how J star changes with average reservoir pressure. Standing suggested that values of J star at different average reservoir pressures are proportional to relative permeability and inversely proportional to the formation volume factor and the viscosity. This is referred to as the relative mobility. With this relationship, a future value of J star, referred to as J star sub F, is equal to the present value of J star sub P, multiplied by the inverse ratio of the respective mobilities. That is, the relative permeability of oil, divided by the formation volume factor and the viscosity of oil at those conditions. Combining these relationships into the Vogel equation, Standing found that future IPR curves could be plotted from the equation shown here. Don't be dismayed by the equation. The approach is quite simple. First, we assume a value for the future average reservoir pressure, at which we would like to know an IPR curve. Then we calculate a value for J star future. Knowing these terms yields an equation in Q and P sub WF. This will give us the future IPR curve.
So what we're saying is that Vogel's type curve can be used for our well's IPR curve at the original reservoir pressure. This will give us the present value of J star, which we need for Standing's technique. We then use Standing's technique to obtain IPR curves at lower pressures. There's a good example as to how this calculation proceeds in Nin's text. This has been difficult going, so why not take a few moments to be sure you understand the technique. In 1973, Fetkovich proposed an alternative method of calculating IPR curves for solution gas drive reservoirs. He assumed that two-phase flow occurred through a uniform, circular, horizontal reservoir. More specifically, he assumed a constant outer boundary pressure that is below the bubble point. One of Fetkovich's key assumptions was that the relative permeability to oil, divided by the oil viscosity and formation volume factor, varied linearly with pressure, as shown here. The straight line, to all intents and purposes, passes through the origin.
Fetkovich was able to show that the production rate divided by the average reservoir pressure squared minus the bottom hole flowing pressure squared equals a constant, J sub O prime. At the original reservoir pressure, P sub I, the flow rate equals the difference of the squared pressures times a constant, J sub OI prime. J sub OI prime is a function of effective permeability to oil at the original reservoir boundary pressure, P sub I. Saturation is constant for the well being analyzed. J sub OI prime may be thought of as a replacement for J, the productivity index. With these equations, it is not difficult to plot the IPR curve at a given reservoir, or boundary pressure P sub R bar. Let's now solve the same problem that we did earlier, using Vogel's method. Assume that the production rate is equal to 1,172 barrels per day, when the bottom hole flowing pressure is 716 psi. The original average reservoir pressure was 1420 psi. By inserting these values into our equation for J sub OI prime, we are able to calculate a value for J sub OI prime of 7.73 times 10 to the minus fourth. So now we have an equation that will give us the flow rate as a function of bottom hole flowing pressure and can generate the IPR curve for the original reservoir pressure. We may now calculate the potential, Q prime, of the well under these conditions. Q prime is equal to 1,571 barrels per day. For comparison purposes, you will remember that we calculated a value of 1,684 barrels per day using the Vogel technique. The agreement between these two methods of calculation is generally good in the intermediate pressure ranges, but there is often deviation at the outer ranges of pressure rate axes. Major differences between these methods will be discussed later in this module. However, either method may be used with the assurance that the results from the other will not differ dramatically. To learn how Fetkovich's method is used for calculating future IPR curves, we must assume that J sub OI prime will decrease in proportion to the average reservoir pressure. When the average reservoir pressure drops below P sub I, a new value of J sub OI prime, referred to as J sub O prime, can be calculated using this equation. So in our example, if the average reservoir pressure dropped to 1,000 pounds, the value for J sub O prime would be equal to 5.44 times 10 to the minus fourth. Knowing this value of J sub O prime for an assumed future value of the average reservoir pressure P sub R bar, we have a new IPR equation as shown here. The equation for the rate versus bottom hole flowing pressure at this average reservoir pressure would look like this. Fetkovich's method yields two equations, one describing the initial reservoir performance and another describing performance at an assumed future average reservoir pressure. From these two equations, we can calculate values for J sub O prime and plot IPR curves for any future average reservoir pressure. Here, we see the two curves from the examples we just solved. We would proceed in the same manner if we wanted to find another IPR curve at a lower value. Now would be a good time to be sure you understand Fetkovich's method. We may now summarize what we have learned about the IPR curve. Above the bubble point pressure, it is a straight line. But as we reach the bubble point, it begins to curve downward as gas comes out of solution and inhibits flow. As the average reservoir pressure decreases because of depletion, the IPR curve decays, as we see here.
Both Vogel and Fetkovich's methods are limited to solution gas-drive reservoirs and assume idealized conditions. So let's take a moment to discuss what options are available in the event that such idealized conditions do not exist. We'll discuss such factors as skin effect, reservoir heterogeneity, differential depletion, and the drive mechanisms other than solution gas drive. It is important to understand these restrictions and not to apply these curves inappropriately.
Let's begin by discussing skin effects. The skin effect is a near wellbore phenomenon. In the ideal flowing well, that is, one that fully penetrates the formation, where the full formation is open to flow and where no formation damage or stimulation exists, the pressure profile during flow looks like this. The drawdown, equal to the pressure drop in the wellbore, is equal to P sub R bar minus P sub WF. However, if the formation near the wellbore has been damaged because of drilling fluid invasions, there will be an additional pressure drop at and near the wellbore because of this damage. This same additional pressure drop exists if the well only partially penetrates the formation, or has limited perforations, or if turbulence exists in the formation near the wellbore. Because this additional pressure drop occurs near the wellbore, it is called a skin effect, and is referred to as delta P sub skin. The total pressure drop in a damaged well is equal to P sub R bar minus P sub WF, plus delta P sub skin. Because a damaged well causes an additional pressure drop, the skin effect is said to be positive. If the formation near the wellbore has been enhanced, say by fracturing or acidizing, rather than by damage, then the drawdown will be reduced. The reduced pressure drop is again referred to as delta P sub skin, but this time it is negative, and the skin effect is negative. The total pressure drop in an enhanced well is equal to P sub R bar minus P sub WF minus delta P sub skin. The magnitude of the skin effect, and whether it is positive or negative, is obtained by conducting special well tests. Full details appear in Unit 3 of the video library program on gas well testing. These tests will give us a value for delta P sub skin, and knowing its value, we can calculate the flow efficiency of the well. The flow efficiency is equal to the pressure drawdown of the ideal well, divided by the drawdown of the well with skin effects. Flow efficiency will be equal to this relationship, which we see will be less than 1.0. For the enhanced well, the skin relationship will be negative, and the value of the flow efficiency will be greater than 1.0. Standing has prepared a series of curves which allow us to calculate the IPR for wells which have flow efficiencies different from 1.0. Using these curves, we can calculate the IPR of a well if the damage were removed or the well stimulated. His curves are shown here. The vertical axis is the dimensionless pressure of a flowing well, and the horizontal axis is a dimensionless flow rate, specifically the flow rate of the well divided by its maximum flow rate without damage. The curves are drawn for flow efficiencies from 0.5 to 1.5. Let's apply the standing curve to our well that is producing at the rate of 1,172 barrels per day, with an average reservoir pressure of 1,420 pounds, a wellbore flowing pressure of 716 pounds, and we assume for the moment that the flow efficiency is 1.0. We can calculate the maximum producing rate from this well when no damage exists. Starting on the vertical axis at 0.504, which represents the dimensionless pressure, we intersect the flow efficiency at 1.0, and then move vertically down to a dimensionless flow rate of 0.69. This ratio is equal to the producing rate of the well divided by the maximum producing rate of the well without damage. With a producing rate of 1,172 barrels per day, and this ratio of 0.69, the maximum producing rate without damage is equal to 1,698 barrels per day. This is very close to the result found earlier from Vogel's curve, and represents the inherent inaccuracy of reading curves. Let's assume for the moment that the same data applies, but now we have learned that the flow efficiency is equal to 0.7, not 1.0. We enter our dimensionless pressure at 0.504 again, move horizontally to flow efficiency 0.7, and then vertically down to a dimensionless flow rate of 0.525. This tells us that the maximum production rate when no damage exists would be equal to 1172 divided by 0.525, or 2,232 barrels per day. As expected, this well has a greater production potential. We know the maximum rate without damage. Now we must find its value with damage. Because it is damaged, we know that its maximum flow rate will occur where the bottom hole flowing pressure goes to 0, along the 0.7 flow efficiency line. This is at 0.87 times the maximum flow rate. So, for a damaged well, the maximum flow rate will be 2,232 multiplied by 0.87, or 1,942 barrels per day. With this information, we can plot a Vogel IPR curve for both the damaged and undamaged well. An additional curve could be calculated for an assumed flow efficiency greater than 1 to account for well stimulation. If, for example, a flow efficiency after stimulation of 1.5 is assumed, then we would use the 1.5 flow efficiency curve presented by Standing. Since we know the maximum producing rate without damage, we can calculate the expected producing rates after stimulation and develop the appropriate profile. By comparing producing rates before and after stimulation with the cost of the remedial work, we could assess whether it is economical.
We can summarize by saying that skin phenomena cause an additional pressure drop near the wellbore, which is either positive or negative. The skin effect may be measured by performing multiple rate flow tests. Once we have determined its magnitude, we may calculate a well's flow efficiency, and then, using Standing's curves, calculate Vogel-type IPR curves. By assuming flow efficiencies for a damaged well before and after stimulation, we can see what the IPR curves would be under those conditions and determine whether stimulation is economically beneficial. Up to this point, we have considered the shape of the IPR for a single homogeneous producing zone. In reality, however, this is hard to find.
Now, let's look at the reservoir inhomogeneities. Many horizons are separated by relatively thin but highly impermeable horizontal shale breaks between the productive intervals. Production from and fluid data of any one layer may not be the same as those from other layers contributing to the production from the well. Consider an example in which a well is completed in a horizon having 3 zones, one with a permeability of 1 millidarcy, the second of 10 millidarcies, and the third of 100 millidarcies. It will be assumed that there is no vertical communication between these zones in the reservoir. Initially, production will come principally from the 100 millidarcy zone, with the smallest contribution being from the 1 millidarcy layer. Thus, after the well has been producing for several months, the most permeable zone will be the most depleted and at the lowest average reservoir pressure, while the least permeable zone will be the least depleted and at the highest average reservoir pressure. Consider the case where the average reservoir pressure in the 100 millidarcy zone is 1,000 psi, that in the 10 millidarcy zone is 1,200 psi, and that in the 1 millidarcy zone is 1,500 psi. The well is now tested at various production rates to establish the IPR. If the IPR of 1 millidarcy is like this, the 10 millidarcy like this, the 100 millidarcy like this, then the gross IPR curve is the sum of all 3. A point on the gross IPR curve has a flow rate which is equal to the sum of the flow rates of the 3 individual curves. In general, then, a well producing from a stratified formation because of differential depletion will exhibit a gross IPR like this. That is to say, an improving productivity index with increasing production at lower rates, but a deteriorating productivity index at the higher rates. But consider a well completed in a two-layered horizon, where water breakthrough has occurred in the more permeable, more depleted layer. In such a circumstance, the watered-out zone has the higher permeability but the lower pressure of the two zones. Let's assume further that the watered-out layer produces 100% water, while the other layer produces water-free oil. Beginning with the oil zone's IPR and adding the water zone's IPR, we obtain the gross IPR. At any given bottom hole flowing pressure, we can read off the oil rate, the water rate, and the gross production rate. This allows us to calculate and plot the water cut as a function of the gross production rate. The water cut is zero until we reach a bottom hole flowing pressure low enough for water to flow. Thereafter, the water cut at any pressure and flow rate is equal to the ratio of the water production rate divided by the gross production rate.
We've now examined the Vogel and Fetkovich equations for solution gas drive reservoirs. We've seen that they can be modified to account for a number of variations, including skin effects and, to some extent, reservoir heterogeneity. Both methods have been shown, through use in the field, to be valid for solution gas drive reservoirs. Empirical tests, however, have shown that Vogel's curves are less accurate at lower average reservoir pressures and lower rates.
Maximum error of 10 to 15% will occur if a low drawdown, low rate measurement is used to extrapolate this curve to the 100% drawdown rate. In addition, the following limitations apply to both the Vogel and Fetkovich methods. They apply only to solution gas drive reservoirs. Where other drives exist in combination with solution gas drive, results may be good under certain conditions, but only below the bubble point pressure. They are applicable only to two-phase flow, though again under some conditions. Agreement with three-phase flow systems has been good. All results should be subject to field comparisons and history matching techniques. In comparing the two methods, it should be noted that the Fetkovich curves generally result in higher flow rate performance predictions than do Vogel's curves. Fetkovich's method of predicting future IPRs is simpler than the standing Vogel method, as it does not require making material balance calculations, nor the prediction of relative permeability values. It yields reasonably accurate results as well. Before completing this module, we should offer a practical procedure for conducting an inflow performance. First, shut the well in and conduct a pressure buildup test. This will give you the average reservoir pressure. Second, with a recording pressure gauge on bottom, place the well on production at a low rate, and after ample time is allowed for the rate to stabilize, record the bottom hole flowing pressure. Third, flow the well at two successively higher flow rates. Let each rate stabilize, and note the bottom hole flowing pressure. Fourth, after the last test is run, shut the well in and conduct another build-up test. This test will give 4 points on the IPR curve. Unfortunately, this test requires a great deal of time, and so for economic reasons, we often have only sufficient time to conduct a single flow test.
A single flow test and a value for the average reservoir pressure is sufficient for flowing and artificial lift well predictions. However, the complete multiple flow test provides more accuracy. It should be remembered that with a knowledge of the basic reservoir and fluid properties, pressures, downhole hardware, and completion data, computer models can be used to generate the appropriate family of IPR curves for a given well. In such calculations, no limiting assumptions about flow equations, reservoir descriptions, or fluid properties need be made. you should review your company's capabilities in this area. The next module is devoted to vertical lift performance. But before proceeding, this would be a good time to review the concepts and problems presented in modules 1 and 2.
This program has been sponsored in part by the following companies: Agip, Aramco, City Service, Dome Petroleum Limited, Gulf Oil Corporation, Mobil Oil Corporation,